So let's talk fronts and thunderstorms. First of all, look at this picture here. What do you see? Well, you'll notice you got a chunk of air here that's got a lot of clouds in it. And over here we got a chunk of air that doesn't have a lot of clouds in it. That means there's two different air masses, and this point right here is where the air masses are meeting. And that's where our action happens with the weather. Remember, we talked about where two different air masses meet. Something's got to give. Some of the air's got to go up, which is more likely to make it form clouds and then subsequently precipitation. And if this happens violently enough, you can get what we call a storm. So a front is where our air masses meet, and air masses can meet a couple different ways. First of all, we can have this. We can have stationary warm air. Think about us here in Georgia. We typically have nice warm air, typically holding a fair amount of moisture because that's what warm air can do, can hold more water. And we get this continental polar air mass coming down from Canada. We get that cold air pushing towards us. Well, when these two meet, something has got to give. Well, when the cold air meets the warm air, what's going to happen? Well, we know warm air tends to like to rise anyway. So the cold air is going to displace the warm air. And it is going to push that warm air up because the warm air is lighter, cold air is more dense, so it's going to stay down near the surface. Well, in doing so, that's going to cause some action. The warm air is going to go up. It's going to make the water in the warm air condense, form a cloud, and then subsequently precipitation. And if this happens violently enough, if there's enough push from the cold air, you get a storm. Here we can actually see what's going on here. Well, this is my cold air from Canada, and you can see it's pushing really hard down to the south. That right there is my front, and that's where the action is going to happen. That's where the air is going to be pushed up violently and make clouds quickly and make precipitation happen a lot more violently and severely. So, with a cold front, what happens is that the air gets pushed up very quickly, and the water in the air goes up very quickly, and it's likely to form clouds and precipitation. Now, I want you to take notice of the dashboard of my car. It is 71 degrees when I'm at mile 798, but now I'm at mile 804. I've gone 6 miles, and you'll notice the temperature went down 7 degrees. Now, I didn't go up a mountain. I didn't go down a mountain. I've just gone horizontally. And what happened? I must be going from one air mass into another, going from warmer air into colder air. Now, this was coming home from Florida one year, I think at Thanksgiving. So I was in Florida, and the air over here is nice and warm and humid. It's Florida air. And as I was coming back into Georgia, I crossed that front. I crossed that point where the cold air was coming in and the temperature dropped 7 degrees. And this is what it looked like. In a course of only a couple miles, I went from nice, clear, sunny skies. And in those 4 miles, I'm now crossing over to where I'm meeting cold air. So I'm at this border here where the cold air is now coming in. And my nice warm air is being pushed up by that cold air. And all of the water that warm air is holding is now being forced to condense and make a cloud. And as this happens a little bit more violently or quickly, we're going to get those clouds growing too big, too fast, and they're going to drop their precipitation quickly and violently, and that's what a storm is. So here's a graphic of what happens with a cold front. Cold front comes in and it makes the warm air go up, and right along the cold front, you tend to have clouds, rain, and violent precipitation. Here you can see it on a weather report going from 60 and 27 to 37 and 22. And you'll notice we've got rain because if the temperatures are going to drop this much, that means cold air is coming in, and it's only doing it in one day, 60 to 37. That's a big temperature change. It's going to push the air up very violently, and it's going to make rain 100% chance all across the area. So here we go. Summary of a cold front. Cold air pushes into warm air. Warm air is pushed up. It's going to make clouds. One thing about cold fronts is they move a lot faster than the warm fronts we're going to talk about because cold fronts have a lot more pressure. They can push fast and do things more violently. And cold fronts tend to form storms. And we draw those on the map using this symbol. Now, the opposite of a cold front is a warm front. This is when warm air pushes into cold air. So imagine I'm someplace and I'm just sitting here and I got nice cold air and warm air is trying to come in. Well, what happens? Well, warm air can't make the cold air rise because cold air is more dense. So instead, what happens is my warm air winds up kind of sliding over the top of my cold air. Well, now we know that up here it is colder. My warm air that has a fair amount of water in it is going to have that water go up a little bit higher where it's a little bit colder. So the water in my warm air is now going to condense and form clouds and precipitation. The difference with a warm front and a cold front is how quick and how violent this happens. A warm air mass doesn't have the pressure, doesn't have the push of a cold air mass because it's not high pressure, it tends to be low pressure. So when a warm air mass comes in, it just kind of slowly slides over the top of a cold air mass. It can't push it out of the way, make violent stuff happen. So the warm air does this a little bit more slowly. So we get rain forming that's a little bit lighter, a little bit slower, a little bit longer lasting, and not as violent as with a cold front. So in summary, warm front is this. Warm air mixes into colder air. Now that's a key distinction here. Cold air can push warm air out of the way very quickly and violently. Warm air can't do that, so it just kind of sort of slides over this top and starts to mix with the cold air. When that warm air rises over the colder air, it's going to form clouds because it's going up to where it's a little bit colder, and it's going to now mixing with colder air, which is going to make its water condense, form clouds. The difference with the precipitation is you don't get storms. You get longer, slower, easier precipitation, but you don't tend to get storms. And they are shown on a weather map. Notice the color tends to be in red because we're talking about warm air coming in. So that's why we color those red, whereas cold fronts are colored in blue. Now the changes with a cold front versus a warm front. You'll notice here that this is still a cold front. We went very quickly from 60 to 37. And in a very small area, we're getting that rain and that precipitation and happened very quickly. However, notice the changes with a warm front. Over here in the cold front, it went down 23 degrees in one day. But with warm fronts, it goes from 46, and then it goes to 54, and then it just goes up a little bit every day. It goes up 4 degrees every day. Warm fronts are slower than cold fronts because it takes time for that warm air to mix with the cold air, whereas cold air can just instantly push all of your warm air out of the way. And you know this to be true. You know that this can happen, that we can go from nice warm day to the next day, bam, it's cold. But the opposite does not usually happen. If we're cold, it takes a couple of days for a warm front to make us warmer. Now, the precipitation that is associated with a cold front and a warm front. Now, movement of fronts, they don't move at the same speed because they're moving and mixing and pushing on each other different, but they are always moving. Now, with a cold air mass, right here's where my action is happening. But remember, the cold air is pushing in, so my area where this action happens winds up over here because the cold air keeps moving that direction. So imagine you were standing right here and you get some precipitation. Well, a few hours later or the next day, you're just standing in cold air now, and the precipitation is now further away from you because fronts move, because air masses don't stay in one place. Now, you can also have a situation like this where a cold front and a warm front hit one another. Imagine that a cold front doesn't quite have the pressure. It's run out of gas and it can't totally push the warm front out of the way. But the warm front is also starting to slide in. Well, in this case, this is like a convergence situation where both sets of air are going to try to be pushed up. And nobody's winning the battle. So it happens that right here in this one spot, the air masses are meeting and nobody's winning the battle. All the air is going up. This is what's called a stationary front. Stationary front means that you get two air masses meeting, but one is not moving the other. So it stays in place. It stays stationary. That line where the air mass is meeting stays in one spot. The precipitation along a stationary front is not typically violent because they're kind of going back and forth, and it's not like the cold front can push the warm front out of the air so quickly. But you get a lot of rain, and it stays in one place. So you get a lot of rain in that one place because the front is not moving on down the road. A stationary front is drawn with this symbol because it is the combination of a warm front and a cold front that stays in one place. Notice the symbols are on one side. It's indicating that the warm front is moving that way. That's indicating that the cold front is trying to move the other way. Well, they're moving opposite directions. This means that they're pushing into one another. Here's the problem with stationary fronts. You typically get flooding because with the other types of fronts, it rains and then it moves on. Tomorrow it's moving on down the road. But with a stationary front, all the rain stays in one place, and you get too much rain falling in one place, and that leads to flooding. Now you can also get this kind of dynamic. This is obviously a warm front. Got warm air trying to push into colder air. Get that now. However, sometimes you can get a cold front, say a really strong cold front that's moving really fast, and it hits the warm air from behind. Well, that's going to help push my warm air up really, really quickly and really, really violently. So here we've got three chunks of air meeting. It's not really entirely a warm front because I've also got cold air pushing in. This is a special type of front called an occluded front. An occluded front is when cold air catches a warm front from behind. And this is the nasty type of front. This is when we get a lot of action going on. This is where you get really violent weather is along these occluded fronts. They're shown on the weather map with this symbol. It's kind of a purplish, but the symbols are drawn on the same side because it indicates that both sets of air are going the same direction. These are the types of fronts that gives us our tornado or our worst, nastiest type of weather. Now let's talk about that nasty weather. We're going to look at thunderstorms first. What is a thunderstorm? By definition, I know you know what it is. You've experienced them here, but a thunderstorm is one that is producing lightning and thunder, hence the name thunderstorm. But more specifically, these are ones that come from cumulonimbus clouds, those big puffy but stormy puffy clouds. They produce strong winds and heavy rain and give us thunder, lightning, obviously, but also can produce hail. Now, not all thunderstorms are the same. They are primarily different because of their size. First of all, let's look at a single cell thunderstorm. I've got one cloud here, and you can see all of the rain coming out of the bottom of the cloud. This is off the coast of Florida where you can see the horizon. You get it, okay. When it's only one cloud, we call that a single cell. Sometimes you can see single cells around here. Here's one. Here's my one cloud, one big cloud. Otherwise, the sky is clear. And on the radar, you can see there it is. So I've got one small little thunderstorm. It could be violent. They could be dangerous. But it's a thunderstorm caused by a single cloud by itself. Now, a multi-cell thunderstorm. Here we've got three thunderstorm clouds that are starting to merge together. Well, now it's not a single cell, it is a multi-cell. Here you can see three rising cumulus clouds that are very close to one another, and they're kind of merging together. This is called a multi-cell thunderstorm. A little more violent because we've got more air moving around. It's also impacting a bigger area. A squall line. A squall line is that's what it says. It is a line of thunderstorms that tends to form right along the boundary of a front because you have basically a wall of cold air that is pushing into the mass of warmer air. So you get a kind of very well-defined line of thunderstorms forming. You can see them here. Here's my cold front coming in, and out ahead of the cold front, it's making my warm Georgia air go up very violently and make thunderstorms right along the leading edge of that cold air coming in. You can also have what's called a supercell thunderstorm. Now, a supercell thunderstorm is basically a huge, powerful, nasty storm cloud, cumulonimbus cloud, that has a mesocyclone at its center. These are like, just what they said, They are super cells. They are super sized, really massive single cell thunderstorms. They look like this right here. They look like a bomb going off. Now, for this to happen, you kind of get the sense here that we must have a lot of water rising. And when it gets up here, you can see how my cloud kind of fans out like this, because it's basically just sucking up all of this air and this water and making my cloud grow very, very violently. Well, if we've got that much air rising, it means we've got a spinning pattern of air. We got like a vacuum cleaner in the middle of this cloud, just pulling up all of this air and water, and it grows and it gets bigger and it gets stronger. Well, that pattern in the middle is what's called a mesocyclone. It's not exactly a tornado, but you can kind of already predict how this helps tornadoes to form. A mesocyclone is a rotating column of air that you find inside of a supercell thunderstorm. And the bigger the supercell, the more powerful that mesocyclone is, and the more air and water it pulls into the storm, the bigger it gets and the more violent the storm. Now, where do these supercells form? They typically form here in the Midwest. Why? Well, that's because that is kind of ground zero, where we have these two air masses meeting most violently. That's also right up along the point where the jet stream seems to fluctuate back and forth. So here's a summary of our thunderstorm classification if you didn't pick up on it. However, thunderstorms just don't magically appear out of anywhere. They develop over time, and they form and develop in very specific patterns. And we know this because we live here in Georgia and we experience thunderstorms all the time.
What you see behind me here is the first step in the development of a thunderstorm. Notice this big cloud here. It's a big white puffy cloud. Well, those are called cumulus clouds. And this is actually the cumulus stage of thunderstorm development, because all thunderstorms have to start with the cumulus cloud. Now, that's a big collection of water. This is a hot summer day, and that hot air is rising and taking water up into the sky, and it's building this cumulus cloud. Eventually, the cloud's going to get big enough and full enough with water that it can form a thunderstorm. So once again, the first step in the formation of a thunderstorm is this cumulus stage, and it involves the cumulus clouds growing and getting bigger to the point where they'll hold enough water to cause a thunderstorm.
So if you ever see these types of clouds, see these nice white puffy clouds, but they have this vertical appearance to them, and we see these all the time, especially in the summer when it's nice and hot. These are all rising cumulus clouds. This is not a storm yet, but this is the cloud growing, and as it grows, it'll eventually get too big and then can cause a thunderstorm.
So this right here is the mature stage of a thunderstorm. You can see there's a lot of rain coming down. You can see the trees moving around because there's all that wind caused by the rain pushing the air as it moves to the ground. There's lots of thunder, lots of lightning. This cloud got too big, and now it's dumping all of this water that it can't hold anymore. Once this thunderstorm cloud runs out of water, it will move into what's called the dissipating stage of thunderstorm development. So once again, this is the mature stage of a thunderstorm. It's the middle stage, the second of the three stages of thunderstorm development.
So even though it's not actually raining right now, you can tell there's a thunderstorm close by, and that's because of how windy it is. Somewhere very close to us here, this thunderstorm is dumping a lot of water out of the cloud to the ground. And as that water falls out of the sky, it pushes the air out of the way, which makes it very windy. So when you see this kind of effect here, you know it's time to go indoors.
So now we're in the third stage of thunderstorm development, and all thunderstorms go through these three stages. This third and final stage of thunderstorm development is called the dissipating stage, where the cloud is dissipating, or it's breaking up, or it's falling apart. And you can see that there's not nearly as much rain now. The cloud has already dropped most of its water. And because it's dropped most of its water, it's not pushing the air as strong, so you notice the winds aren't pushing the tree as much. This thunderstorm is basically dying. It's almost over. It's dropped all of its water. It's not nearly as violent as it was just 5 minutes ago. In a few more minutes, this storm is going to be gone. There'll be no more precipitation, there'll be no more thunder and lightning. The storm will have run out of its energy, it will run out of its water, and it'll be over. Once again, this is the third stage of thunderstorm development, called the dissipating stage, which is characterized by lighter winds, less rain, and the dying of the storm.
Now, these are thunderstorms, so they're going to have thunder and they're going to have lightning. So we need to examine those. First of all, what is lightning? Lightning is just static electricity. It's extra electrons that have accumulated in one place until basically it discharges or zaps to another place. Well, how's it formed? Well, it's very similar to shocking yourself with static electricity after you walk across the floor with your socks on, say like in the wintertime. So out there in nature, there are extra free electrons. There's extra free electricity floating around out there. If you think about in the wintertime walking across the carpet, especially in your socks, you pick up or you rub these extra electrons onto yourself. Well, nature doesn't like there to be an imbalance of pretty much anything. Think about this with temperatures and that thermal equilibrium. Nature likes things to be equal. So this person that now has extra electrons, when they touch somebody that doesn't have extra electrons, the extra electrons jump to make things balance. And that jumping of those extra electrons, or that electricity, that's what lightning is. So what happens out there to make a lightning and a thunderstorm? Well, we know that air is rising. And what happens is with some of those extra electrons that are down there low on the ground, well, they get picked up, they get sucked up with the air and move up into the sky with the water and the air that's moving up into the sky. So eventually we wind up with this. We've got this cloud now up here, and it's picked up a bunch of the extra electrons from down near the ground. So now we have that imbalance. We've got a lot more negative charge, a lot more electricity up in the clouds than we do down near the ground. And remember, nature doesn't really like things to be imbalanced. Now, it's not like touching someone or touching a metal doorknob, because this imbalance can get to be so big that literally the electrons can jump through the air. And if you think about shocking yourself on a doorknob, you don't even have to touch a doorknob to shock yourself. All you got to do is get close and the electrons will jump through the air. And that's basically what lightning is. You get so much extra electrons in the cloud that the charge builds up such a big imbalance that it will literally jump from the cloud back to the ground to make things even again. There's a couple types of lightning. The two most common are cloud to cloud and cloud to ground. Cloud to cloud is basically when one cloud zaps another. And you can have two different clouds and they have a different amount of electrons. And it's just like when you shock somebody else after walking across the carpet because you have picked up more electrons than that other person. That's the idea here. I got a cloud here. I got a cloud here. This one has more electrons in it. So when it touches the other cloud, it zaps or it discharges electrons to that cloud. It's called cloud to cloud lightning. Now, cloud to ground is the one that we are a little bit more familiar with. This is now a cloud has too much extra electrons and the ground doesn't, and the electrons will jump from the cloud to the ground all at once to make things equal. And that's what lightning is. It's just that discharge of extra electrons from one place to another. So what is thunder? Well, when those extra electrons try to force their way to the ground, you get a bunch of electrons. And electrons are stuff, they're matter. And you get all these electrons really trying to go to the ground all together at one time. Well, they're rubbing on each other and trying to push past one another as they're getting to the ground. And the more they rub on one another, the hotter they get. So in lightning bolts, you have incredibly high temperatures, up to, say, 50,000 degrees. That's really, really hot. Certainly much hotter than the air is normally. Well, what do hot things do? Hot things want to expand. So when a lightning bolt strikes, and as it's moving through the air, it makes the air super hot. The air expands and spreads out. Well, that's not what thunder is. Lightning doesn't last very long. It's a split second. Well, now my air isn't hot anymore. And what my air does, it tries to contract because now it's not so hot. Well, all of that air that expanded very, very quickly now immediately tries to go right back into this spot right here. And when it does, it hits each other. And that's basically what thunder is. It's the sound you hear when that air, which was really hot and expanded, comes back in and tries to go back into that space, and it hits itself. It is referred to sometimes as a thunderclap. A clap is the air coming back together after it was expanded. It's just like clapping your hands. You move your hands apart, bring it back together. That's what thunder is, except on a really, really big scale. Now, there are some patterns with thunderstorms, some data. Where are thunderstorms most common? Well, as you can see from this graphic, it seems to be a lot more common around the Gulf of Mexico. Well, let's explain why. First of all, remember, you've got to have a cumulonimbus cloud. You've got to have those big rising cumulus clouds, which are big collections of water. And Florida has a lot higher incidence of these thunderstorms, these cumulonimbus clouds, than any other place in the world, certainly in our country. Well, why? That's because the water around the Gulf of Mexico is really, really hot. So the water is going up into the air pretty easily anyway. So it's going to make those cumulonimbus clouds easier because it has a nice, hot, evaporating water source. In addition, we know this about Florida, that air converges over Florida because you have sea breezes on both sides. And as the air hits over Florida, it takes all of that nice warm water up in the air. It's going to lend to the development of very large cumulonimbus clouds very easily. Now, where are thunderstorms least common? You can see from this graphic, they're least common on the west coast and to a certain extent in the northeast coast. We want to explain why. And it's going to be the opposite explanation as to why they are so common around Florida. Let's look at LA, just for some statistics. There's only about 35 days a year where they get any rain in Los Angeles, compared to 109 here in Atlanta and 188 days in Orlando, Florida. So if you only get 35 days of rain a year, that means you're going to have a lower chance of thunderstorms, because let's face it, not every time you get rain, you get thunderstorms. So the rainy season in LA, where they get most of their 35 days, is actually November to March. Well, November to March, that's wintertime. Temperatures are lower, things are cooler. So you can't generate those nice, tall, rising cumulus clouds as easy. So when Los Angeles gets their rain, it's not warm enough for thunderstorms to typically develop. Those numbers I just showed you are actually kind of deceptive a little bit too. In the actual city down here of LA, they get even less thunderstorms. The numbers with Los Angeles are always skewed when we talk about the weather, snow, rain, precipitation, because technically there are portions of these mountains that are in the city limits of Los Angeles. You can be in Los Angeles and turn around, look back towards the mountain, maybe see a thunderstorm. You see snow. So technically it's Los Angeles, but they really get almost no occurrence of thunderstorms in the city. Here we compare some U.S. cities. This is the amount of lightning that they get. And LA is a really big, huge city. 1,200 seems like a big number. 1,200 bolts of lightning within 10 miles of the airport in a year. Well, look at Orlando and Miami and Atlanta. 400,000 lightning strikes in Orlando within 10 miles of the airport. So you get an incredibly high amount of lightning around the Gulf Coast and almost none on the West Coast. You can see the same thing is true with Seattle. Now, once again, I talk about how it is a little deceptive because on the coast, you get almost no lightning. As you go inland from Los Angeles and you get up in the mountains where the air is forced to go up a little bit more violently, you can get some more lightning. But most of the people in the city of Los Angeles don't really ever experience lightning. Check this out. It's on the news. They were on the news in LA and there was a lightning strike. And they were talking about this on the news. Hey, look, everybody, we got lightning. I want you to think about Georgia. Would the occurrence of lightning be a newsworthy story here? The answer is no. We get lightning all the time. But they get lightning so rarely in Los Angeles that when they do, it actually makes it onto the news. And I showed you this before. When it rains hard, like a thunderstorm rain, people in LA don't know what to do because they don't experience it very often. Now, severe thunderstorms. There's about 100,000 of these what we call severe thunderstorms. 100,000 thunderstorms every year, but only 10% are classified as severe. What a severe thunderstorm is the one that has higher winds, can have larger hail and or tornadoes. So these are the nasty, most damaging thunderstorms, and they tend to happen in the middle part of the country, in the Midwest. Reason why is because that's where you can get those superstorms or those supercell storms developing. The supercells are the ones that cause the most damage and more often tend to be severe. Now, lightning. Where is lightning most common? Always around the Gulf of Mexico. Notice, once again, on the California coast, they have almost no lightning at all. And that's because they don't have nice warm water that can feed the development of those rising cumulus storms. Some facts and figures. About 40 million lightning strikes every year in the U.S. You have less than 1 in a million shot of being struck by it. But what we don't realize is that lightning actually causes a lot of damage. 9.5 million, it's almost $1 billion in 2022 of damage caused by lightning. Texas has more lightning strikes than any other state because Texas is a big state. If you throw a dart that represents a lightning bolt at a map of the U.S., it's more than likely going to hit Texas. More of a chance than any other state because Texas is a big state. However, Florida by far has more lightning strikes per square mile and has the greatest number of deaths from lightning. Georgia, interestingly enough, is second in terms of the amount of insurance claims that we have for lightning strikes, only behind Florida, because we get a lot of lightning here because we're very close to the Gulf Coast. Now, people can get killed by lightning. You'll notice there's a trend here, and that is that deaths from lightning are going down because we have such better weather forecasting data and we have such better ways to get people information and warnings about severe weather that if you're outside playing golf and there's a lightning strike in your area, sometimes you'll even get an alert on your phone and you might know then, hey, I'm in danger, let's go inside. Whereas a generation ago, that wasn't the case. More people were killed by lightning. Lightning fatalities by state. Now you'll notice Florida, number 1. Now, why would Florida be so much higher? You notice, California, it says 7, which seems kind of high. Even for a state that doesn't get much lightning, the problem is in California, people aren't used to lightning. You might hear lightning and not know to go inside. It's a big state with a lot of people. So even though it says 7, that's not really a big number when we compare to this 47 in Florida. Now, fatalities in Florida. This is going to sound a little harsh, but Florida got a lot of old people. People retire and go to Florida. Old people, they like to go outside and say, play golf. So you're outside in Florida, you're playing golf, and you have thunderstorms pop up, you're a lot more likely to get struck by lightning. People go to the beach in Florida. People vacation outside in Florida, where you're a lot more likely then to get struck by lightning and hence killed. Now, the cost of thunderstorms and lightning. Like I already said, about $1 billion of insurance claims every year. And about 4 million acres of land burn every year from lightning strikes. So thunderstorms are a lot more damaging than we think. 28 people killed every year. And that's in the US where we have good communication and good technology. You go overseas and that number is a lot higher. Some myths. You're caught outside during a thunderstorm, you should crouch down and reduce your risk of being struck. Lightning never strikes in the same place twice. If it's not raining or there aren't clouds overhead, you're safe. That is not true. If a lightning victim is electrified, you shouldn't touch them. You'll be electrocuted. Definitely not true. Remember, these are all myths. If you're outside in a thunderstorm, you should seek shelter under a tree. No, because a tree is closer to where the source of the lightning is, and it's a lot more likely to be struck. If you're trapped outside and lightning is about to strike, you should lie flat on the ground. That is not true, because if the lightning hits the ground near to you, you're increasing the surface area by which electrons or that electricity can enter your body. If you're in a house, you're 100% safe. Not 100% safe, because lightning can also run through your house. So what time of day are thunderstorms most common? In the late afternoon. Why? Because that's when it's hottest, and that's when those cumulonimbus clouds can get biggest and most likely cause a thunderstorm. What time of year? Well, when is it hottest? In the summertime. The later you go in the summer, the more likely you are to have a thunderstorm, because the ground is hottest, which makes the air rise more quickly and make those rising cumulus clouds.